How's it going, everyone? I'm Nick, and you're listening to episode 41 of the Fresh Perspective podcast. By the end of your life, your feet will have passed through about 1 second of time more than your head. Likewise, if you work on the top floor of a skyscraper, you will age slightly slower than your twin, who works on the ground floor. This isn't all just theoretical math and equations, mind you. It is a real and measurable consequence of the curved and warped fabric of the cosmos that links gravity, space, and time. In this episode, I'm joined by Connie, Sam, Alice, Walter, and Sage in an exploration of the science of time. In our conversation, we consider how humans experience the flow of time, the speed of light, the possibilities of time travel, the so-called twin paradox, the illusion of a force of gravity, entropy, and what happens when we stretch Einstein's laws of relativity to their breaking point. Like our last episode on how we can reduce stress through simplifying our lives, the following is a recording of the first half of a live online meeting of the Free Thought Forum. None of us involved are professional physicists or experts on the subject, but we nevertheless see the value in talking about things at the edge of our comprehension. It's an educational exercise, and one that I'm happy to share with those of you listening in the future. This program is brought to you by your local Free Thought Forum. Our members come together from various belief systems and backgrounds to share their perspectives, hear new ideas, develop positive friendships, volunteer, and learn more about science, philosophy, and life skills. Every meeting is a celebration of free speech, civil discussion, and the free exchange of ideas. We want to ensure that as many people as possible have the opportunity to speak their mind and have their ideas contested and reviewed among peers in an inclusive and supportive community. So we are now authorizing the creation of new chapters around the world. If you would like to start a new chapter in your community, find official events near you, participate in our online meetings, or support our programs with a donation, please visit freethoughtforum.org for more information. Sam, could you please read the title and the introduction question for us?
Yes. The Science of Time, Spacetime, General Relativity, Gravity, and Time Travel. This, of course, is one of our scientific literacy primers. Our introductory question is, if you could visit any location in the past or future, where and when would you go?
I have no interest in seeing the past. I would like to go to the future.
So what in the future would you look forward to, Connie?
I don't know. I don't know what's going to be in the future. That's why I want to see it.
Oh, that makes sense to me.
It's funny. Hey, Alice is joining us again. We're happy that you all finally made it to join us, and the timing is perfect. So everybody's aware, we are recording today. So whatever you say will be permanent, and the entire world is listening to. But the introductory question that we were talking about was if you could travel anywhere in time or space, time travel like in Back to the Future, where would you go? Connie was telling us that she would want to go to the future, and I'm completely in the same boat. I would also want to go to the future.
I was thinking that I would probably want to visit another planet where the civilization is a lot kinder to each other and is a little bit more advanced. So, more spiritually, I guess, homogeneous, where people are able to live in harmony with each other. And so I guess it's in the future, but just on a different planet.
Very cool. Maybe in the past, who knows? This sounds like the topic of a really awesome science fiction. But I'm sorry, go ahead, Walter.
Well, I was going to say I'd like to visit 17.5 billion years ago, the time of the Big Bang.
Did you say just before the Big Bang?
Well, maybe 1 microsecond after.
Yeah.
Why would you want to visit the Big Bang? Well,
it would be neat to see the creation of everything.
I was actually thinking somewhere along the lines of what Walter said, because, there's a lot of things we know pretty darn well. For example, we know very well and have a lot of evidence to support our idea of how everyday life in Rome happened, at the height of the Roman Empire. We have a really good idea of Egyptian life, and so I'm thinking to myself, how ancient should I go, or how far forward would I go? I was thinking I would really like to explore a moment in time that is a complete mystery. Maybe just before the Cambrian explosion, or kind of like what Walter said, right when the Big Bang was finally unfolding. What in the world was going on? What could I see or measure? It's for all that we do know about history. We have this extreme, overwhelming amount of patches of time, where we have absolutely no clue what was going on. So, yeah, I think that's my answer right there.
Sounds great.
One thing I've noticed, so when I was a kid, there was no Wikipedia. There were a lot of things that just were not available for teaching yourself. But in my lifetime, I've seen that greatly improve. But there are some things I can imagine that would be absolutely great in terms of education. Like, I think it would be awesome if you had a program that you could type any question in the world into, and it would shoot back every single writer, every philosopher, every thinker who's ever commented on it. And when, like, let's say some passage from Kant comes up, you could even get commentaries that different people, or you could look at when people have cited one thing or another. The way I kind of visualize it is you have a tree of questions, or you click on a question, you type in your question, you get a tree of possible answers, and you can explore the possible answers in the tree. The tree also has problems with some of the answers, and then there's responses to the problems. You can get literature down at the bottom, but I think if there was something like that, you wouldn't have to spend as much time to learn the same amount of stuff. Additionally, it would be really cool if you had a chat bot at the bottom that you could have philosophical conversations with. And if you say anything technically wrong, it would like immediately correct you. And I think a couple hours of that a day, and you could get in a few months what right now would take decades to accomplish.
To my mind, that sounds just a few steps removed from the holodeck of the Enterprise, where you could go in and say, hey, I want to go to this moment in time. I want to listen to this speaker. Then the computer can fill in all the details about wind speed and temperature and background and costumes. And, like, there's just so much information at hand. I don't know. But what do you think, Sam? Is your idea kind of a holodeck light?
I actually haven't seen enough of Star Trek to know how similar, or like, I really wouldn't care too much about costumes, and I'm more interested in like the philosophical questions. But I mean, it could potentially be used for anything.
Yeah, and I bring that up because, of course, doing research on different kinds of time travel, there's this one prevailing theory or idea where people say we don't really need to bend the laws of physics. We don't need to travel at 88 miles per hour. We don't have to try to force ourselves into a different moment of time. We can just create an extremely detailed simulation, a simulation generated from the best information we have of different moments in time. And then all we have to do is just step into that simulation, like what people do with their AR video games, just kind of experience things in that way. It doesn't strike me as the most glamorous or fun version of time travel, but it definitely sounds doable. It definitely sounds like something that can practically happen.
Yeah, so I liked my idea of like philosophy teaching software that's really advanced. But now that you mention AR, I think just really good virtual reality video games would be another really good benefit of going to the future. In real life, that's probably where I'd spend a lot of my time.
And also the past. Do you guys remember when the Notre Dame Cathedral caught fire? The reconstruction crews actually consulted with the video game software company that created the Assassin's Creed games. Do you guys remember hearing about that?
I remember hearing about the cathedral burning down, but I didn't know that the VR people helped with the reconstruction, that Assassin's Creed was the specific video game that was used.
Yeah. I mean, that's kind of the ridiculous point I'm trying to make is because the video game designers, they went off of scans, from what I understand, of the actual building before the fire. And they also went off of construction plans and other references to recreate this virtual space in this video game, which Connie is a big fan of. That's like one of her favorite all-time games. But those scans and that information, they could then hand over to the government, hand over to, whoever they needed to in Paris. And they used that information to rebuild the real-life actual Notre Dame Cathedral. this is the world we live in, guys. This is pretty wild.
Yeah, I heard a story not too long ago about some college kids that got lost on a college trip where they were in Rome. One of the kids, the tour guide was even with them who lived there. He had got them completely lost. But one of the college kids was able to get them all back through a very complicated route. And everyone was really surprised. And it turned out that the kid knew the route from Assassin's Creed.
Yeah, never underestimate video games, guys. Like that's the lesson of the day. Let's go ahead and keep rolling on the science of time today. Connie, could you please read the first half of the next section, please?
How we experience time. If I have seen further, it is by standing on the shoulders of giants. Isaac Newton. In addition to your 5 major senses, your mind also interprets reality in successive passing moments. In our day-to-day lives, it seems like time is a fixed part of the universe, like the lights on the stage of space where the events of reality play out. We intuit that everyone experiences the same passage of time no matter where they are or what they're doing. This is similar to how Sir Isaac Newton dealt with time and space in his groundbreaking laws of motion. Perhaps his most revolutionary idea dealt with what he called the force of gravity, something that pulls apples to the ground and moons to their planets, roughly like how a rope pulls a tetherball.
Awesome. Thank you so much. I'll go ahead and read the second half of that part. Newton's equations were accurate enough to send NASA's astronauts to the moon and back. They still perfectly fit with the physics of the universe on a human scale. However, they failed when extreme precision was needed. And they couldn't explain certain phenomena like Mercury's strange orbit. Is your sense of the passage of time reliable? Why or why not?
I think one's personal sense of the passage of time is definitely relative to what is going on, the person's perspective during that period of time. That's my personal opinion, is that time can be both relative and very static. But when it comes to personal sense of passage of time, I definitely feel that that's a relative experience and depends both on the person and at what point in time they're experiencing their life, I think.
I agree 100%. And Alice, you can correct me if I'm wrong, but just from what we understand of the human brain, your memory and your experience isn't like what people think. It's not like we're little video cameras that take accurate and detailed measurements of reality. Instead, the well is poisoned, I guess is what we call it in logic. Our experience, it's primed and muddled and interpreted through our emotional experience and our values to a large extent. So if you're enjoying your time with a sweet person on a date, then it might feel like time is just standing still and it feels wonderful and it feels like a night has lasted an entire week because you're having such a great time. There's also time flies when you're having fun. After throwing around a football or whatever, oh my gosh, it's time to come back in. The sun's about to set. When we're stressed out, of course, like we talked about last time, if you're giving a presentation in front of people, it takes every effort in your body to just keep trudging through your speech because all eyes are on you, So our emotions can definitely taint our experience of time for sure.
Mm-hmm. Yeah.
Yeah. And I would also like to add, of course, that certain substances and mind states also disrupt the flow of time. For example, when right as we're falling asleep or waking up, we have a very distorted view of time. As we, slide from one, I guess, state of consciousness to another. People experience similar things when they're on, what's the term, hallucinogenics, and other drugs and things like that. To such an extent where people lose days of time during like a high or something like that, and I don't know a lot of details about it, of course, but it's funny. This sense of time that we all have, it's not accurate. And there are things that can throw it completely out of whack. So yeah, it's kind of wild to think that we still go on with rough estimates. That was about a minute. That was about 15 minutes. We sometimes in our work, we get like a feel for gaps of time. Those should be tentative at best.
As you were mentioning, certain areas of the brain and chemicals do affect our perception of time passage. Like if there was an emergency, you were giving CPR or something, your mind is going to record or incrementally more memories of that instant because of the increase of epinephrine and other neurotransmitters. And those will all be stored in the amygdala. And as a result, when you think back on it, there are, say, more frames to the picture than there would be if you were doing nothing. And I assume if you were up on some big high and lost a few days, it would be a dysfunction of the amygdala, or even the suprachiasmatic nucleus, which takes care of our circadian rhythm.
Yeah, I bet you're right. Yeah, that's incredible. I love that. But let's go ahead and keep rolling. Sam, could you please read the next part for us?
Yeah, I've got you covered. So we're on the speed of causality. We're going to begin with a quote. Conscious ignorance is the prelude to every real advance in science. And that's from James Clerk Maxwell. Inspired by Newton and Michael Faraday, James Clerk Maxwell in 1865 published his equations demonstrating that electricity and magnetism belong to a unified force that moves in waves in a vacuum at about 300,000 kilometers a second at the speed of light. Albert Einstein would later use Maxwell's equations as the basis of his theories. He found that the speed of light was a universal constant and the fastest speed at which matter, energy, or information could possibly travel. Then our question is, what are some of your favorite thought experiments that relate to the speed of light?
I've never studied much about it, but I know that gravitational fields affect the speed of light. Really, I'd like to know more about that.
Yeah, and you're 100% correct. The kid in the front row is anticipating my lesson, Connie. You know, what is this? So here's a thought experiment that's Einstein-esque, is how I would paint it. We know a thing or two about the speed of light, and of course we just learned that it's the speed limit of the cosmos. One rule that Einstein and of course everyone to follow would assert is that you can't add to the speed of light and you can't subtract from the speed of light. So here is your thought experiment. You're on a train, because they're always on trains. Like that seems to be the norm here. But say you're traveling on a train, and this is a fast train. Let's say this train is going, I don't know, maybe 1,000 miles an hour. And it's going 1,000 miles an hour on a smooth, straight trajectory. It's not increasing your speed or decreasing. It's just steady at that 1,000 miles an hour. So you have a flashlight in your hand, and you turn it on. There are photons now released from that light, and they're shooting out in front of you. Now, what is the speed of those photons? They're going at the speed of light. And then you can say, well, hang on, we're going 1,000 miles an hour forward. Aren't they going the speed of light plus 1,000 miles an hour? And the answer is no, that's not how light works. Weird enough as it is, that's just not how it works. Well, now imagine, if you will, everyone, what if we turned around and we shot the flashlight back behind us, so that it's shooting behind the train, the direction of the train. Well, same story there. Those photons are moving at the speed of light, and they don't warm up to it. They don't speed up to the speed of light. They are immediately born, so to speak, born in quotes. They are immediately flying at the speed of light. Well, do we subtract or add any speed from the train? Nope, they have nothing to do with it. And so I would say this is one kind of demonstration that we can do that's purely hypothetical. Another one of the most commonly shared thought experiments from Einstein, he had when he was in high school. I imagine he was extremely bored and daydreaming, like we all are at some point in high school. And he thought about what Maxwell and what other scientists at the time were saying about light waves. The idea that light moves in waves was a new idea. Hey, Sage, really good to see you. We're at the bottom middle of the first page on the discussion primer. But yeah, so Einstein's thought experiment had him running at about the speed of light and looking over at these waves of light. And he thought to himself, well, what if I traveled at the speed of light, or maybe even a little bit faster? Is there a point where the wiggling waves of light, is there a point where they can freeze if I'm going fast enough from my perspective? And he knew, because he was, pretty good at math, he knew that that's impossible. He knew that that's breaking one of the rules that Maxwell had, set forth at that time. So in his experiment, he knew that it's impossible to see light waves as frozen in time. Therefore, nothing could ever be fast enough to have that perspective This isn't the only reason that is a speed limit of the universe, of course, but this is one of those ways that we can get to that conclusion. So yeah, these thought experiments. Einstein had a terrific imagination.
Hmm.
Let's see, Alice, would you be okay with reading that part?
Yeah, sure. Odd quirks of nature. Atomic clocks, such as those utilizing cesium, are far more accurate and precise than any other timekeeping device we've created. This makes them ideal tools for testing time itself. In the famous Keating experiment, identical and synchronized atomic clocks were separated. One was kept at a naval base, while another traveled on an airplane that circled the Earth twice. When the clocks were reunited, they were out of sync. We similarly see that GPS satellites must be programmed to measure time differently so that they reliably and accurately interact with GPS devices on the ground. When lasers from the base of tall buildings hit sensors on their top floors multiple times, we likewise see the same temporal incongruity. In 1919, during the Eddington experiment, we also found that light itself can be warped, refracted, and redirected as it travels through the vacuum of space. What can explain all that? If Newton's laws are incomplete, why are they still used? Newton's laws affect things at a certain level of existence, and maybe quantum physics laws affect things at a different level of existence or something. So they can be useful in one context, but maybe not in another.
They're good enough to handle a spacecraft, but not good enough to do a GPS service.
Yeah. Do you guys agree? What else would you say? Why would we use scientific laws that are definitely incomplete?
Well, engineers do it all the time. A close enough theorem, I guess you'd call it. Sometimes theoretical and things like that just aren't necessary. And we as humans can't be expected to be perfect in everything. But if we want to better perfect GPS and our way we map the systems around us in the entire universe, we will have to be more specific and start using those. Instead of E equals mc squared, use the E equals mc squared plus then several calculus equations.
Yeah, and I like how you put it that, if something is serviceable, if something is close enough, well, then why throw it out? And I think this can remind us on the progressive nature of science, just as a body of information. Just like the quote with Isaac Newton at the beginning, every scientist basically stands on the shoulders of those who came before, even though, for example, something like alchemy, is completely, whack and it's largely nonsensical. There are a few gems in alchemy that were later carried over to create the science of chemistry. A lot of the more mystical and nonsensical parts of astrology were borrowed and eventually evolved into astronomy. Of course, astronomy and chemistry are way more disciplined and, way more reliable than their predecessors. But, we don't throw out something because it has some mistakes. We keep the parts that work and move on. And I think this is something that's largely forgotten when we when we talk about the history of science. But let's go ahead and keep rolling. Sage, could you please read the next part for us?
All right, general relativity. I have no special talents. I am only passionately curious. Albert Einstein. In 1915, Einstein published his theory of general relativity, in which he introduced a new and radical concept of reality. He proposed that an external reality underlies our collective experiences of the space between things and the time between events. This reality is modeled as a four-dimensional fabric of the cosmos known as spacetime. Spacetime can be warped by matter and energy. Its effects on objects vary depending on their relative speed. Therefore, there is no universal standard for measuring the passage of time. Every measurement is relative to the observer's frame of reference. And as we move faster through space, we move slower through time. And when we move slowly through space, we move faster through time. And while we can all agree on the number of ticks made by our respective clocks, we each experience the length between ticks differently. Space-time tells matter how to move. Matter tells space-time how to curve, according to John Wheeler.
Yeah, so we have a great deal to chew on in that part. I'm curious, what are some of your impressions, thoughts, and comments on just that synopsis of the theory of general relativity?
Yeah, I wanted to comment on a misunderstanding that I had in college. It took me a long time to grasp. So we often talk about how time slows down if the observer is moving, but of course, in physics, you don't have to pick. So let's say you have somebody on Earth and they get into a spaceship that are traveling away from the Earth. You can pick the Earth as a reference frame. You can also pick the spaceship as your reference frame and pretend that the Earth, it's not even so much pretending. You say that the Earth is actually the moving object going away from the spaceship. We use the spaceship as kind of our frame of reference. We're saying we're using it as our zero location, and we talk about the Earth traveling away. Well, because of this, there's something that arises called the twin paradox. So, in terms of time slowing down when you're a moving observer, one of my favorite descriptions of this, which may not be perfect, but I think illustrates it really well, is on the spaceship. Let's say you had a telescope on Earth, and on the spaceship, they're watching a movie. If you're on Earth and the spaceship is going away from you at a speed that is some fraction of the speed of light, you're going to see the movie, of course, playing in slow motion. But the thing that's very weird is that if you had a movie playing on Earth and the people in the spaceship are looking in a telescope back at you, the people on the spaceship would actually see the movie on Earth being played in slow motion as well. And this is where the supposed paradox arises. From both people's points of view, the people in the other place are experiencing time more slowly. And so it seems like an apparent contradiction arises. But of course, there isn't a real contradiction here. The contradiction comes from a misunderstanding, but it can be very difficult to wrap your head around how it's possible that both people are experiencing time slower, depending on what you choose as your reference point and how this all makes sense.
Yeah, as I've been studying special relativity and general relativity, one question keeps popping up, and that is to whom, and according to what? Because classical physics, we can say that, this thing is accelerating, or, in your physics class, everyone's obsessed with talking about bouncing balls. So, like this ball bounces in that direction, and this took 10 seconds, and this was so many feet above the ground and accelerated at this velocity and all this type of stuff. When we get to Einstein and beyond, we're now burdened with this very important question, and that is, well, according to whom? Are you going from the reference frame of the person throwing the ball? Are you going from the reference frame of someone in an airplane looking down? All these things are important because time isn't like that curtain or that light that Newton was comfortable using it as. It isn't just this fixture of the stage of the cosmos. Time is something experienced very differently with every person. I have my clock that's ticking slightly different from your clock, or time feels like it's passing slightly faster than, for the people on the top floor of a building than the bottom floor, or maybe it's slower. I better be careful about that. but let me say that it's just different. It's literally different. If you're traveling faster or if you're further away from the center of gravity of the Earth, then your sense of time is not perfectly in sync with everyone else's, which is a huge deal. This is something that shatters a lot of our ideas of just how time and space works. But that's not the most fun part of it, in my opinion. when we get to this idea that the cosmos, that space itself is like this fabric, this four-dimensional space that gets warped and twisted, and that warping and twisting makes all sorts of weird things happen. Oh man, that's where it really gets fun, guys.
Actually, I wanted to follow up on kind of my description of the twin paradox. What Nick was mentioning, I think about not just it being clocks, but also how you actually experience it, actually applies here to the twin paradox as well. It's not just going to be that a clock is going to run slower, but if you were to send somebody out on a spaceship going near the speed of light, they would actually experience time more slowly, and they would not age as quickly. But, when you go back to what I was talking about before, with you can pick whatever reference frame you want, you could look at one of the twins on the spaceship going out from the Earth. You could talk about him moving, but you could also talk about the Earth moving away from the spaceship. So anyway, the paradox comes because both people think time's happening more slowly. When they return, it's not possible for them both to be younger than the other. There's a contradiction. Does anybody have any ideas about how the twin paradox is resolved?
As I understand it, and this is kind of from an interpretation of reading the Ender's Game sequels, that the spaceship, as it goes faster than the I have to think about this before I say it, but if you end up on the other planet and then fly back, you're going to probably see your grandparents. So what you've done is you have bent time in a way that they traveled a further distance I'm not so pleasantly spoken or well spoken as your grandparents did. So you essentially did warp time or took a different path through it.
Yeah, I think that's a legitimate way to look at it. The person so in Einstein's ideas, you can talk about moving through time. You can also talk about moving through space. The person who is on the Earth, they're just traveling through time. But the person who leaves and returns is traveling through both. Their path is a little bit different because they're kind of moving sideways. Mm-hmm. But the really technically accurate way to resolve the paradox actually has to do with the frame of reference. Basically, the person who leaves and returns, they turn around. That turning around makes it so that you can't treat them as a stationary observer. If they were going the same direction the entire time, then you can use that as a reference frame. But once you have the turning around, there's an additional reference frame. And of course, this is all stuff that physicists talk about. It's a little abstract, but that is pretty much how the paradox is resolved.
I wish I'd written down the equation while I was reading up on some of this stuff. But it was the fourth dimension, d4 is equal to I times c times dt. So the speed of light, of course, is involved. Then the irrational number is involved as well as time. Does that have anything to do with this portion of the discussion? It's all kind of new stuff to me.
Well, yeah. Well, Walter, I'm actually really happy that you brought up the speed of light because it's trying to resolve problems with the speed of light and making sure that it's always constant. This is part of what led Einstein to say, oh my gosh, we need some wiggle room. We can't add or subtract, speed from light. That's, it goes against all of our physics even today. So, gosh, where can we find this wiggle room so that kind of like in that analogy I was talking about before, where you're on that train, and you're pointing the light ahead of you or behind you. How can all of the laws of physics be satisfied when you have these things that seem to contradict? And the wiggle room is, time is experienced slower by one person or faster by another person. So I'm not sure if the twin paradox that I'm familiar with is the same as the one you're familiar with, Sam. But in a nutshell, the way I understand it is you have twins, born on the same day. One gets to stay home and live out a normal life, relatively still, just sitting on the earth. Of course, the earth is spinning and all that jazz, but, the second twin leaves and gets to get in a spaceship, and this spaceship is a super sci-fi spaceship that allows them to travel at way high speeds, close to the speed of light. Well, because space-time is both space and time, and they have this kind of relationship, I don't know if technically it's an inverse relationship. Maybe, Sage, you can correct me if I'm wrong with that, but they have this relationship where if you really lean into one, then the other side doesn't affect you as much. So basically, the person staying stationary on Earth, they're basically leaning into time. Time is going to affect them very dramatically. They're going to feel the effects of time and they're going to age they're just going to age regularly like the rest of us. But since the person traveling up in the sci-fi spaceship, since they're traveling so fast and they're really leaning into that traveling through space, time is going to affect them less. Time is still moving, but the effect of time on them is experienced very differently. And when the second twin gets done with their trip and they come back home, they're going to look a lot younger. They're going to feel like they've only been gone maybe for a shorter amount of time because according to what they felt, their experience between the ticks of the clock, it hasn't been that dramatic. Whereas the person who was more or less stationary, they really felt those moments, between ticks, and time has taken a much more dramatic effect on them. So that's the version of it I'm really familiar with. But, I could be slightly off. Did I get anything wrong there, gentlemen?
No, so yeah, your twin paradox is the same one that I'm talking about. The only thing that I would stress that kind of really brings the paradox. So you talked about kind of moving through time or space, and that limits how much you're moving through time. In terms of doing the math in a physics problem, you can say that the spaceship is stationary, and if you can ask the question, how much time is passing for the people on Earth in relation to the people in the spaceship? What's really weird is the twin on the spaceship, looking back, if he could see what's happening on Earth, from his perspective, the Earth is moving at the speed of light, away from him, even though he's technically what we would think of as moving. In terms of doing the math, it's perfectly fine to say that the Earth is moving at near the speed of light. And so you can say that the time is moving slower for the people on Earth from the perspective of the people on the spaceship. You can also say the other way around. From the perspective of the people on Earth, time is moving slower on the spaceship. That's where the paradox arises. And this is all in special relativity. None of it you don't have to pull in any general relativity, but that's what makes it so weird.
And even though these are weird, I'd like to circle back to the fact that these aren't just hypothetical. We've been talking about thought experiments, but like the section we read beforehand, where we have quickly moving satellites that are distant, far distant compared to us, from the center of the Earth, from the center of the Earth's gravity. They literally do experience, even though these are non-sentient objects, they experience the flow of time at a different rate than similar computers that are just sitting here on the Earth's surface. So, as obscure as this all is, it reflects a very real phenomenon in our day-to-day lives that, sometimes we have to do a little digging to find where it manifests, but it's real. It really happens, and time really does tick differently, so to speak. We're going to talk a little bit more about people having different frames of reference. Later, we're going to talk about black holes, and that's all very interesting, of course. Let's keep rolling, unless, of course, does anyone else have anything they wanted to add real quick?
Yeah, actually, there is. So this is something completely different than the twin paradox. There is an analogy. This could have actually been used for the thought experiment question, but a physics teacher shared this with me, and I thought it really illustrated the idea really well. So let's say you're in a train car and the train car is completely sealed off. There's no windows. You've got a thick wall, a thick roof, a thick floor on every single side. You have a science lab. You can put anything you want in that science lab, any tool, any experimental thing. You can perform any experiment, but as long as the train is moving at a constant velocity, there is no experiment that you could do inside of that train car that would let you know you were moving, unless you were to cut a hole in one of your walls. But as long as you're stuck inside, there's really no way to tell that you're moving.
Yes, very good. That leads very well into our next section that Walter was actually anticipating very well. Walter, could you please read for us the section "Gravity is not a force"?
Gravity is not a force. When you're riding in a car and the driver presses down on the accelerator, not that I'd ever do that, it feels like a force pulling you back into your seat. What is that force? Well, it's an illusion. You are holding still relative to the ground. The car is accelerating forward, thus creating the illusion of force. The theory of general relativity reveals that the so-called force of gravity is a similar illusion. When objects are drawn to each other, like an apple to the ground, no force is present. This phenomenon is a consequence of matter interacting with the bizarre curvature of space-time. The more massive an object, the more it warps the fabric of the cosmos, resulting in a stronger gravitational pull. Which brings up a very theoretical question on my part, but let's first discuss,
Yeah, and I real quick, I want to point out for anyone listening that gravitational pull is in quotes, force is in quotes, because it's kind of like that tetherball example at the beginning. It makes so much sense, not just mathematically and practically, but just in how we picture things going around other things in the solar system and in the universe, it makes sense to picture them like connected with a rope, connected with a string, something like a tetherball. But that's a completely wrong way to look at it, especially when we're trying to take space-time into account. So here we are. we live in a reality where there's not this magical thing sucking an apple down to the ground. Instead, we have the shape of the universe itself, the shape of here's a term also in quotes, the fabric of the cosmos. Space itself is warped in such a way that things that are a part of space-time, not resting on space-time, but that are a part of space-time, as they move through time, are drawn towards massive objects. It's a phenomenon that's super counterintuitive. And not just me, but several science teachers, I'm sure, around the world, we have a hard time describing this phenomenon because, again, it's counterintuitive. It's one of these parts of the universe that is under no obligation to make sense to us. It's under no obligation to ring true with what we experience. But nevertheless, the math bears it out, and our observations from rigorous experimentation bears it out as well. So, it is what it is.
Yeah, actually, there's another example I could give from that's similar to my previous one. When we were talking about special relativity, I mentioned the train. But there's an idea that's very similar where instead of a train, you have an elevator, but the elevator doesn't have constant velocity. The elevator is accelerating. And same thing, you have a science lab in the elevator. The elevator's got thick walls. You're not allowed to look outside. One of the ideas that I think Einstein talked about with general relativity is that the acceleration that you experience in terms of, a lot of times in a physics class, you'll talk about like the acceleration due to gravity. When talking about how much the Earth is pulling you down, that's, the units are the same as acceleration. Well, if you're in an elevator and there's some acceleration due to the elevator accelerating, there is no way to distinguish that acceleration from the same type of acceleration that you would experience from a planet pulling you down, which I think is a very weird thing.
Yeah, and again, you're exactly right on the money, Sam, because it is indistinguishable. And so, kind of like what we were talking, Sam, before the meeting today, that's a bit of a logical fallacy, when you say, well, this thing certainly exists and this other thing certainly exists, but you know what? There is absolutely no way to tell them apart. But they're definitely two separate things. They're not the same thing, definitely. That should raise a few eyebrows. And that was Einstein's problem. It's like, okay, look, you're all telling me that this thing, gravity, exists, but it acts and it behaves just like acceleration. So convince me that I'm wrong, prove to me that gravity is a thing. And of course, we can't. He's exactly right. It's basically acceleration. And then we have to get into the uncomfortable question of, well, what is accelerating? Well, again, to answer that, we have to realize that space-time is warped and everything is riding space-time, I guess, kind of like bubbles ride a wave in the ocean. Space-time, especially as we progress through time, it's warped and bent and, this odd, what's the word, topography that makes things behave in a certain way. I heard a YouTuber just the other day, was awesome. He described it in this way, that just like if you shoot an arrow or if you're running down the road or whatever, you have this momentum, you have this direction and you have this energy of moving in that direction. Well, we could think of our progress through time as that type of thing, as a type of energy, a type of momentum, a type of direction. We're moving through time relentlessly, like an arrow flying through the air. And one way to think of gravity is when some of that time movement is converted. This is a word you're not really supposed to use, but I'm going to use it anyway. It's converted into spatial movement. And this is one way to think of gravity. And so there's, like I said, it's difficult to get the idea across sometimes, but that's just because it's not something that's common to our everyday experience.
What made me understand the idea of acceleration is the fact that not only is the Earth doing it to me, but I'm doing it to the Earth. I am causing gravity that I create from my mass is pulling in quotes, the Earth towards me in infinitesimal amounts of measurement, I'm sure.
Yeah. it's a non-zero amount. You're exactly right. So, that's like what we see with this is an example that deals more with surface tension, but you have astronauts up in the International Space Station where objects will, buzz around them, and, water will creep up their arms when they're wringing out a wet rag and things like that. Like, your gravity is something. Now, on the scale that I just described, it's probably not noticeable, but that still doesn't mean it's zero. and it is absolutely true that when you step towards the earth, when you fall, quote unquote, again, when you fall toward the earth also falls a little bit towards you. I mean, this is all completely consistent with physics as we understand them. But yeah, we should probably, before we get too turned around, we should probably keep on going. Let's see. Connie, could you please read the next part for us?
Is time travel possible? I have noticed that even those who assert that everything is predestined and that we can change nothing about it still look both ways before they cross the street. Stephen Hawking. We are all time travelers slowly progressing into the future. It is possible to accelerate your relative experience of the forward flow of time. However, by exploiting gravity's effect on time, a person on the event horizon of a massive black hole, for example, will see time race past them, while far-off observers will perceive them as frozen in time. Traveling near the speed of light on a spaceship could also make years to your friends back home pass like mere minutes to you.
Thank you so much. Let me interrupt to say real quick that, oh man, if time and if gravity and if space-time, if these are fascinating topics, everything then gets dialed up to 11 when we talk about black holes. Let's take Einstein's theories and let's dial them up and let's take them to their max. Let's stretch them out as far as they can go and see what happens. And if I'm correct, black holes, we didn't even know that they existed, right? I mean, weren't they predicted by Einstein? I don't know.
Yeah.
Do you guys know about that?
They were predicted but not discovered until later.
Yeah, like I wonder, maybe Einstein doesn't get all the credit, but I know that his equations allow for him. We only got the first picture, so to speak, of a black hole, gosh, like 4 years ago or last year. Maybe it was just last year, but yeah. But of course, we've been able to detect them with I think X-rays or radio waves before that. Sage, you would know a lot more of that than I would, but yeah, these bizarre quirks of nature. I found another talk that described the physics as they possibly could be beyond the event horizon, beyond the edge of a black hole. And inside of them, there's this really neat idea that it's totally possible that space-time, the laws of space-time, the laws of relativity, they flip. And you get a phenomenon of time-space. You're in this new realm where time acts like space and space acts like time. And oh my gosh, when I heard that, it just floored me. Like there are a million science fiction books that need to be written about this. This is fantastic stuff.
I can't even imagine what you're talking about. Like, how can space act like time?
Well, in the first way is that, none of us can escape time. I mean, we can all agree on that, right? Like, time is something that's pulling on all of us and leading us all in one direction, right?
Mm-hmm.
So you cross into a black hole, and now the gravitational forces and just the physics of the black hole have now made it impossible for you to do anything or go anywhere other than in one direction, and that's to the center of black hole. It's like entropy or like the second law of thermodynamics. Like, this is a absolute surety. You can only now go to the center of the black hole. What goes in doesn't come out. Unless you're talking about Hawking radiation, but we're not talking about that today, guys. Hold back. But yeah, that's just one example. I mean, this is something that definitely, it's a lot of fun to read into.
Of course, what you're talking about is the singularity, right?
Yeah. In singularities, let's address the elephant in the room. Singularities is where the laws of physics as we understand them, the theories of special relativity and general relativity don't work very well. Singularities are a big problem in physics, which lead a lot of physicists, actually. There's a bit of contention here. They say that, well, therefore they must not exist. Whenever we think of singularities, maybe we're wrong to do so, which is totally possible. Or our tools are just not sophisticated enough to deal with them. That's also a possibility. That with things like quantum mechanics, we're better able to deal with singularities. But yeah, I was surprised in my research. I thought I would find a lot of great evidence of how time began at the Big Bang and how, the singularity that kickstarted the Big Bang at time zero fits really well into Einstein's equations. But what I found is that it gets absurdly complicated, and it actually is hard to make the equations predict a lot of specifics about the Big Bang. And so therefore it leads people to think, well, maybe we're missing a few gaps here. Maybe there's some things about the Big Bang that we don't understand. And, thanks to particle accelerators like what we have at, CERN and thanks to quantum physics, we're getting really close to understanding that. But there's still a lot of room to go before we can understand things, as well as we understand the moon going around the Earth, or the Earth going around the sun, or even Mercury, going around the sun. We get so far with Einstein's theories, but there definitely are still some gaps, just like there were gaps with Newton's physics.
Well, this kind of brings up the thing that I started thinking about, and now I'm developing in my head. We know that the closer we get to speed of light, time changes, but also we know that mass has something to do with that too, changes the speed of light, the amount of gravity. It could possibly be that once you hit an almost infinite mass source, you could flip the time and the space coordinates on the space-time continuum.
Maybe Sage, you can help me give an intelligent answer to that. But all I can say is a lot of things break when we get too close to the speed of light. In some equations, you have to have infinite mass to be fast enough to get faster than the speed of light. And infinite mass is just illogical, so it's probably impossible. You have certain things that are riding on that line. Like I said, Einstein needed to make things work. He needed to basically balance the equations, just like you did in your pre-algebra class. He needed to make things work. And the only way to make those work is to have the speed of light be a constant, and then everything else is more or less flexible around it. I'm being super general here, of course. There are other constants that are just as important as the speed of light, of course. It's not the only one. But a lot of things, I think the word break is the right word. A lot of things just no longer make sense when we get to that speed of light. And you're exactly correct. The speed of light itself is warped. And in my mind, it's, by gravity. In my mind, it's a lot like when light is warped just through simple refraction. Like when you put your straw in the glass of water, it looks bizarre because you have some kind of warpage going on there. The light, there's a trick going on there. And space-time does a very similar thing, especially when you have very massive objects that have a very strong gravitational influence, like the sun or the Earth or a black hole. There's this phenomenon called lensing, where distant objects actually ruin our ability, or not ruin, but they they interfere with our ability to see things where they really are in deep space, because we say, okay, well, that's where it looks like they are. But then we have to take into account that the gravity along all these large objects around the way, there's a lensing effect. They're warping the light just a little bit. So now we have to make calculations to see where this light really is, where these planets really are. It sounds like a big mess, but people with really advanced math degrees are able to make it work. So there you go.
Yeah, I had some wild speculation that I wanted to combine with some of your ideas, Nick, if y'all are okay with me doing that.
Yeah, that's why we're here, bro. Go for it.
There's a kind of a fun idea that, of course, this isn't my idea, and I don't even remember who it is from. So, Walter, you mentioned that, black hole is a singularity. And of course, the other place where the laws of physics tend to break down, where we see a singularity, would be the time that you want to go to, the beginning of the universe, the Big Bang.
Mm-hmm.
So the theory that this one physicist came up with, that I can give somebody a reference for where to find it, but it is this idea that you have kind of these baby universes inside of black holes. And if every black hole contains its own universe, according to this idea, perhaps our universe would be a black hole. So maybe this universe we're in is a black hole, and this forward movement of time that Nick was talking about, how if you're in a black hole, you are being dragged to the center. Maybe the future of our universe is the center of a black hole, and us going into the future is us being dragged to the center of a black hole. maybe we're already trapped in one.
I like that.
Oh yeah. Yeah, I mean that's a lot of fun, and that of course opens up the whole can of beans, guys, because we've been talking only about our universe, and as far as we know, we're the only one there is. However, kind of just having fun with what you just said, Sam. If there are other universes, we can't just assume that they still progress through time in a way that we progress through time. For me, I'm traveling through time at 1 second per second, according to my own reference frame and all that good stuff. If I stepped somehow into a different universe, would time then be unfolding? Will events predate their causes in a different universe? Would that be like twice as fast or like 10 times as forward? Would it be like, hitting 10 times X fast forward on your Roku or whatever? Like there's nothing that says that our laws of physics will be the same. And so yeah, that's just a really fun, fascinating thought. Again, this is so much we're just giving away all these fun ideas for science fiction here, guys.
Yeah, are any of you familiar with who is it Sean Carroll, that's his name, the physicist? He wrote a book, From Eternity to Here. There is a problem with entropy. Entropy is a scientific idea that things always get messier. Of course, there's many definitions of entropy, and they're a lot more technical than the one I'll give here. But the idea that your room's going to tend to get dirty, instead of like things being in a nice, neat little row, as time progresses, things tend to get scattered all over the place. You can, one analogy that he uses, or not analogy, this is a real example, is you can, break open an egg and scramble it, but you can't take scrambled eggs and turn it into a nice, neat egg. Now, of course, you can, in some cases, in a certain system, you can clean your room, but when you're cleaning your room, you're hitting air molecules. You're going to you're breathing out, you're generating waste. And so ultimately, even though your room is getting clean, the universe as a whole is getting messier and messier. So things tend to get disordered. This is, if there's one law of physics that there's probably no counterexample to, this is it. It's not ever going to get neater. It's always going to get messier. But this, of course, creates a problem because you have this real ordered state at the beginning of the universe. But the question is, if you have like this perfectly ordered state at the beginning, what could you have before that? And one of the solutions that Sean Carroll comes up with in his book, From Eternity to Here, the solution he comes up with is the multiverse idea, that the ordered state in the beginning of the universe was just like some local area in another universe, and that it's bubbling off. So even though my previous thing was a pretty wild speculation, it does solve one particular problem. It's the forward arrow of time, or the constant increase in entropy that we've got to deal with.
I've heard in discussions about just the physics of time, I've heard it described exclusively in terms of entropy, in terms of this process of order to disorder, which I find very interesting. I don't think I would go so far as to say that's exactly what's happening. Who knows what the causal relationship is there, right? Like, is entropy something made by space-time, or is space-time something altered by entropy? Like, I don't know, man. I don't know. I couldn't tell you. But I'm glad you brought it up, because I was in a debate not too long ago where someone was talking about entropy as kind of a checkmate atheist type of a thing. And what I mean is, they say, well, if everything goes from order to disorder, well, then how can you explain evolution? How can you explain the formation of planets and the formation of stars? You can't explain it. It's impossible. But one very common thing that a lot of people don't understand is that, just like with what we're talking about here with frames of reference, you have to consider what are the parameters of what you're talking about. For example, can life evolve on Earth? Can you have very complex and ordered things arise even though it's swimming against the grain? Although people will disagree with that. I've talked to people who disagree. They say that no, life and evolution is itself an acceleration in entropy, which which I love. That's a very fun way to look at it, I think. But the answer is, well, we didn't start with a whole bunch of energy and then everything just gets dispelled. The Earth kept getting fed by energy. You know, we have a sun, we have stars, we have cosmic radiation that alters DNA. We have several things that kept inputting into the system. It wasn't a closed system, and the Earth still isn't a closed system. So yeah, the laws of entropy, they're still there, man. we're not violating them. We just have to understand that there's a difference between open systems and closed systems for sure. But yeah, I just realized that I got us on a huge tangent because I wanted to geek out about black holes. We haven't even finished that second to last section. So right now we're on the paragraph that says, "But we can travel." Would anyone like to pick up where we left off?
I can do it.
Sweet, go for it.
But can we travel backward into the past? It may violate the laws of physics. Stephen Hawking also famously held a party to which he invited any and all time travelers from the future. No one came. As far as we can tell, backward time travel is impossible.
I feel bad for him, man. In Stephen Hawking's book, he was really disappointed. He's like, "Oh man, I was really hoping to meet like Miss Universe of 2058 or something, you know, like he wanted to meet people from the future. They didn't show up, guys. How disappointing. All those bottles of wine going to waste, but no, he definitely had a great sense of humor, but what a wonderful experiment. So let's, just to make sure we maintain the experiment, let's make sure that we still promote it. Hey, everyone in the future, if you could travel through time, definitely go back and see Stephen Hawking, if you have a minute. He'd definitely appreciate it. But in all seriousness, kind of like what you were talking about before, Walter, whenever we flirt with this whole faster or equal to the speed of light business, a lot of things just don't work. A lot of our equations become nonsensical. And so, yeah, we have mountains and mountains of evidence, I guess you could call it, mathematical, reasons to suggest that backwards time travel is impossible, as far as we know, because that's the way science works. Sam, could you finish up that section for us, please?
Yeah, except I did want to take a minute and invite any future time travelers to this Discord meeting that we're having. Maybe it's impossible to actually go back in time physically. Maybe it's or technically difficult, but maybe sending a signal back, connecting to a Discord server from the future, maybe sending light signals back into the past would be easier. And so maybe that'll make it easier for people to join our server than it was for them to go to Stephen Hawking's party.
Hear, hear.
Of course, I'm just wanting to say this because if 3 or 4 people just randomly join us from Meetup or from hearing about it, then we're immediately going to ask if they're from the future.
Nice.
But anyway, I don't think either one's going to happen, so I'll go ahead with the last paragraph. It is possible, however, that the past and the future already exist in a form of block time. The present moment may be an illusion we experience, like a reader enjoying a single page in the middle of a book that has already been published.
So, several physicists are okay with the idea that just like how Jupiter exists somewhere out there, out in space-time, Proxima Centauri is out there somewhere in space-time, well, the future is somewhere out there in space-time. They're comfortable with that idea. I mean, why not? Who are we to say that it's not somewhere already out there? However, this immediately strikes many of us, especially when we're interested in philosophy, with this problem of, oh gosh, well, if it's already out there, if it's already written, like the end of a book that we're reading, oh man, does that mean we can't change our future? Oh man, we really stress out about that. We have just one section left. Who would like to read that?
I guess we'll finish it here.
Sweet, thanks, Sage.
Relative limits. Was time created by the Big Bang? Why does matter warp space-time? What is it like inside a black hole? To answer these questions, scientists today turn to the study of the super small that builds on Einstein's work, quantum physics.
Dun, dun, dun.
Oh, indeed. Yes.
If you have enjoyed this conversation or have learned something from it, please leave a like, subscribe, and share it with other open-minded people. All of those small things really do make a big difference and help others find our organization and our podcast. Thank you. That is all I have for you today, but the conversation continues across social media and in the comment sections below. Do you agree with today's message? Am I mistaken about some detail? What feedback or ideas do you have for this program or for the Free Thought Forum? Feel free to share your perspective.